All right, welcome back. This is example 4 of 18822 for Math 365. We are given a cascade tank system where initially tank 1 has 1 gallon of salt per gallon, 1 pound of salt per gallon. Sorry about that. And then each of the other 2 tanks have no salt in them initially. They're just pure water. So that the flow rates in and out of each of the tanks is 2 gallons per minute. And they each have 5 gallons in them. And so our question is, if we assume complete mixing in each of the tanks, find and plot the salt concentration in each tank as a function of time. Okay, we're looking at trying to measure how does the salt get distributed over time for the system. And let's dive in then. Okay, so let's let x1 equal the pounds of salt in tank 1, and then x2 will equal the same thing, pounds salt in tank 2, and no surprise here that x3 should be the pounds of salt in tank 3. Okay, all right, so those are going to be the variable that we're looking for. And so we're trying to measure the rate of change of salt in. So the rate of change of salt will be the rate of change of salt of any of these in particular will equal the rate of the in, whatever we want, 1, 2, or 3, minus the rate of the other one out. Okay. And so one way to think about this is that this is we're looking at the accumulation in pounds per minute of salt. So thinking of it in terms of accumulation, this is pounds per gallon. Okay, and we're going to multiply it by gallons per minute. Minus this is coming in, and then pounds per gallon or times the gallons per minute coming in. Okay, so this is the rate of the salt coming in, and then the rate of the salt coming out. Okay, all right. So let's take a look in particular at tank 1. Tank 1. Then for this example, so dx1 dt, the rate of change in the salt concentration. There is no salt coming in. This is pure water coming in. So that's going to be 0 minus the rate of salt leaving. And that's going to be the amount of salt, x1, divided by the initial amount that's there, which is 5. Okay, times the volume of water coming in, which we know is 2 pounds per minute. Okay, and this is the amount of pounds per gallon. Okay, which gives us that our tank 1 rate of change is going to be 0.4 times 1 times 1. Okay, all right. So this is the rate of change of salt in the problem. In other words, all the salt initially in the problem is the salt that's already pre-dissolved in tank 1 here. So it's pure water coming out. There's 1 pound of salt per gallon in tank 1. As the water is coming in and flushing out, all the water is being mixed, and so that we would expect that this salt concentration in tank 1 would decrease over time as it gets diluted and the mixing continues to happen, so that the flushing of the system continues to occur. Okay, all right. So in this situation, this is a separable differential equation. We can actually solve directly for x1. We can write this as dx1 over x1 is equal to dt. And then, of course, you have the negative 0.4 there. So you can just leave that on the side of negative 0.4. And that's right from here. All right, so if you integrate and solve, you get x1 as a function of t is going to equal some initial amount, e to the negative 0.4 t. Okay. and we know that at t equals 0, that x1 is equal to 1. And so you plug in, that's going to mean that implies that A, our concentration is equal to 1. So x1 of t is then just e to the negative 0.4 t. Okay, so that explains or shows that how the amount of salt is decreasing in time, which then kind of starts a cascade of results. Pretty straightforward. So let's look at tank 2 now. Okay. So in tank 2, the rate of change of salt concentration, dx2 dx3, is going to equal the same amount. So it's going to have some salt coming in the amount of x1 divided by the 5 gallons that is there, times 2, rate of change of coming in, minus the amount of salt x2 leaving, pound of salt divided by the total concentration times 2 there as well. And so this becomes 0.4 x1 minus 0.4 x2. But we know what x1 is, and so we can write this as 0.4 e to the negative 0.4 t minus 0.4 x2, which is the first order differential equation in terms of x2. So it's an integrating factor problem, and so if we solve for x2, we get with the initial condition that x2 of 0 is equal to 0, this implies that the x2 solution for t is equal to 0.4 t e to the negative 0.4 t. Okay, so that's how that solution is changing. And now look at tank 3. All right, looking at tank 3, we find that the rate of change, tank 3, with respect to time, is going to equal the rate in, which is coming from x2, divided by the total amount, times the number of gallons coming in per minute, minus the rate out, which is the rate leaving, the amount of salt leaving divided by the total gallons, times 2. Plugging in, we get 0.4 x2 minus 0.4 x3. We know x2, so we can substitute that in. And so that gives us that this is 0.4 times 0.4 t e to the negative 0.4 t minus 0.4 x3. And then again, this is a integrating factor problem, multiplying everything through. So finding the solution to x3, this implies with the initial condition that at x initial, x3 had no salt mixing in it. We get x at 0, it's 0. So then that implies that, of course, x3 of t is going to equal 0.08 e squared e to the negative 0.4 t. Okay, all right. So our rates of change then for each of the corresponding salt concentrations over time for them is, for the third cascade, it is 0.08 t squared times e to the negative 0.4 t. Here you're going to get 0.4 t e to the negative 0.04, 0.4 t, and then of course x1 is here. Okay, so those were the three rates of concentration changes over time for the different salt amounts in each of the three cascades. Okay, I hope that was helpful. I'll see you in the next video.